Thank you, Mekti. Hi, everyone. Is it working? All right. Thanks for being here. I'm Palina. I'm the CTO at Runtime Verification, and I'm here to talk about some of our recent experience with doing infrastructure audits beyond smart contracts and share some practical advice that I hope you guys would find useful. So what I mean by crypto infrastructure, essentially the whole execution stack that enables the interaction between the user and the smart contract. If we do look at an example that is here, which is deploying smart contract source code, we'll realize that it does go through a lot of different components, and it would be good to make sure that they are actually implemented correctly. So, for example, the smart contract first goes through compiler. It gets compiled to bytecode that is included in the transaction deployment. It is being sent to the JSON RPC node, and it should be up and running for that to happen. Then it gets included in the mempool, then it gets included in the block. Finally, the instructions from this bytecode actually get processed by the virtual machine, where it is also very important that these instructions are being executed correctly, and the blockchain state gets updated. So I did list some of the examples of the components from this execution stack here, like compilers, nodes, virtual machines, consensus protocol, the whole ZK VM infrastructure, and there are a lot of them, and that is pretty much the point I wanted to make, that all of this is code that is governing whether your interaction with the blockchain is actually safe. I did include this picture because I find it funny, and it is true that smart contract security has been pretty much the spotlight in this industry in the past years. But to be fair, we do get a lot of inbound requests for this, like infrastructure types of audits recently, and I think that is genuinely the trend in the industry. So I think protocols actually do security seriously these days. So why do I want to talk about it in general? Like, what is the difference between these types of audits and the smart contract audits? And there are a few, fundamental factors that are different, and the first one being the code base size. So different from smart contracts, where a few thousand lines of code is pretty much the whole project, these code bases are very different. I ran CLOC a couple of days ago on some of the clients, and here's what I got. Like, RIF, the Rust implementation of Ethereum client, is 97,000 lines of Rust, and that is like the modular, compact, efficient implementation of it. Geth, the Go implementation, is even bigger than that. Lighthouse, the consensus client, is 150,000 lines of Rust code. That is excluding tests. You might think maybe there is a problem with like Ethereum infrastructure that is so big in size, but if you look at Fire Dancer, which is Solana client, that is even bigger. It's 340,000 lines of C and C++ code. And of course, like with smart contracts, generally the current, the idea of the audit is that someone, like an engineer, looks through every single line of code, but that is infeasible if we are talking about, this magnitude, this code bases. So we kind of have to find some more efficient solutions. I mean, infeasible in the time frames that we usually, operate with realistically when we are talking about audits. So there are some solutions to this. I'll get back to them later. One more thing I want to highlight is that there are also different threat models and areas of concern when we talk about this type of software. So different from smart contracts, we do take care of things like chain split, denial of service, memory exhaustion. It depends, depending on the purpose of the component we're looking at. We also are trying to identify different potential issues. Like in the case of consensus, we are worried about like leader election. We want it to be fair. We want it to like not be gamed. We want consensus and execution layer to be aligned. So all these sort of things that we have to consider. And in addition to that, these components can also be implemented in different languages that have different memory safety. So just a lot of things to be familiar with. So what techniques, like what instruments do we have for actually reviewing? And well, generally all the usual suspects, similar things to smart contracts. So first of all, of course, manual review. This industry is pretty big on that, and like having a human actually look at the code is still, I think highest guarantee that we can get other than formal verification. But it does scale, as we've discussed, to this size of the code base, so we have some other techniques that we can use to scale this. Like static analysis, testing, fuzzing. I'll talk a bit more later. So what do we do with manual review? The thing we do at runtime verification is we found that for us, the best thing to do is to have like a sequence of shorter engagements where we do very focused manual review on high property code portions. Having this like 6 to 8 weeks does help us avoid like auditor burnout. And then in addition to that, it also gives the chance to the developers to like fix some of the issues we've identified in the previous round, and then we can move on. So how do we figure out what are the high priority code portions we are looking at? Depends on the project, but it can be newer code. If some components of the code are well audited and tested, we can focus on like points of interaction to make sure that they interact well between each other. If we are looking at something that has a reference implementation, like there is a client for an EVM chain, and then there is like an EVM compatible chain, we are looking at if there is some difference between them, then that is something for us to focus on. Like one example being if like an EVM compatible chain has a different gas pricing, like if it reprices some of the opcodes, then it might lead to the denial of service, so we want to look at it like really carefully. And then of course, like really important code, like really important or unsafe. So one example being that Rust generally is considered a memory safe language, but there is a keyword unsafe that helps you like avoid some of the safety. So what we did for one of the project is we went through all the mentions of this unsafe keyword, and we made sure that the assumptions that developers are making about it being safe are actually true, and we documented all of this. And then also another approach to like identifying what is really important is to define a set of properties or invariants that are critical for this particular piece of software. That is why we strongly advocate for doing a design review first. So we spent a few days or a week, depends on the project and the timeline, trying to understand really well what does this project do and whether the design makes sense, and try to identify some properties, put together the specification, because it does help a lot in informing what is the review being focused on. In addition to that, like to scale it somewhat beyond just these key points we are looking at with manual review, we also use tool-assisted review. There are static analysis tools, depending on the language, like Cargo Audit scans dependencies in Rust projects, which is very important, especially considering this like recent influx of supply chain attacks. And we do use AI quite a lot to look at like other parts of the code bases. So like anything that we don't do manual review of, and that as well. Just so we get, just in case it can uncover some more issues. And honestly, it does. We are working with Almanax, that is like an AI tool for smart contract and like not smart contract infrastructure security as well. And yeah, it's been working really well for us. It does identify issues. One trick that we've learned is that work better if you provide specification. So if you try to ask it to not only find vulnerabilities it can think of itself, but also the difference between the specification. And one example of an issue we found this way, that cannot be more specific than that, but essentially it found a bug where the function was making assumptions about something, like some input being validated in the upward function that was calling this one, but it wasn't. And it would be really hard for the AI tool to, well, just infer it in the first run. So yeah, having the specification helped a lot, and that is something that we actually come up with during the design review stage. So yeah, it has been extremely helpful with like both parts of this process. Then what else can we do? So fuzzing is another well-known technique, extremely efficient, really nice way to also scale the security guarantees that you are trying to provide. So there are different flavors of fuzzing. We do all that I am mentioning here, but the first one is panic-focused. So that is like you try to invoke parts of the code base, like you call functions. You try to interact with the nodes through RPC, and then you just feed random, pseudo-random inputs, and you hope that it crashes. So that is what fuzzing is. It helps identify different types of vulnerabilities, like out-of-bound access, resource exhaustion, all types of crashes. The example that I have here is not from our review, and it's not blockchain specific, but I couldn't help, I think it would be illegal for me to not include it. That is from the Cloudflare issue that disabled half of the internet on Tuesday. And the reason for that was that there was a panic in unwrap call in Rust that is like a panicking function, so it just crashed with the bad input. So that is exactly the type of issues that we are trying to prevent with this type of fuzzing. We can go beyond that. We can do property-based fuzzing, where not only we make sure that when we call the function, it doesn't crash, we also assert something about what it actually does. So one example of that that we did in our audits was round-trip conversion between types. And I think, so generally the idea is that we convert some value to one type, then we convert it back, and then we make sure that the result is the same. We can do, we can serialize some value and deserialize, make sure it is the same, and we can also do more high-level stuff that we can come up with if we do design review properly. And then one more type of fuzzing that I really want to mention is differential fuzzing. So differential fuzzing involves running two pieces of software alongside each other and checking that on all inputs they do behave similarly. That has been proven very extremely efficient in identifying bugs. It does require having a reference implementation. So it depends on the situation. We can set it up differently. So one type of differential fuzzing that we have been doing is running different clients for the same chain alongside each other, making sure that they do not disagree. Because if they do disagree, then some of the nodes are rejecting a transaction, the other considers valid. It can lead to chain split or halt or God knows what. So some example of that is checking that ref is behaving similarly to Geth. The guys from Sigma Prime also published a report about a very nice engagement that did a very similar thing to one of the L1s, so I highly recommend checking that as well. And we did find an issue where essentially some of the node implementation for Solana was rejecting empty transactions and the other wasn't, so that is obviously an issue. We can do that for just different chains that, for example, are EVM compatible, making sure that the parts that are common between two blockchains really do behave similarly. We can check if implementation adheres to specification, if you do have specification, or a formal model such as KVM, which is our EVM implementation in K, that is the formal language. Or you can just, generally, if you have two implementations of the same thing, you can differentially fuzz it. So we did this for the Rust implementations of WASM interpreter, and it also helped identify some of the bugs. So a couple more notes on fuzzing. Obviously, the setup is very language-specific and component-specific. An important thing to keep in mind is that it has to be meaningful. So some examples are that in order to test asynchronous execution, we really want to have more than one transaction or more than one blocks, depending on what is asynchronous there, because we want to make sure that we exercise the execution path that correspond to that functionality. If we are looking at the virtual machine that executes instructions, then we actually want to feed it valid instruction sequences that would mimic the actual code that is going to execute. And of course, depending on the language you're working with, that is going to be different. So if you work with Rust, to generate these structured inputs, we use arbitrary. That is a crate that has been very helpful. It is different in Go, so there is the whole toolkit attached to every language. Every language, as I mentioned before, has its own potential issues. So we didn't really find a better solution than just spending a lot of time looking at making sure we're really familiar with the code base, with what the protocol does, with the specifics of the languages we are working with. And then another thing to keep in mind is that when I'm talking about design review, understanding the protocol is very important, but that is something where AI has been also extremely helpful for us. We have been using DeepWiki quite extensively, especially in the earlier stages of the engagement, when just trying to put together a good idea of what the project does, what are the components, how they interact with each other. So that being cross-validated with the client team has also been extremely, extremely helpful in speeding up this process. And well, I wouldn't be myself if I didn't mention formal verification. So that is the process of mathematically proving that the software is correct. As we all know, probably software formal verification is challenging, it is resource-consuming, time-consuming, requires a lot of groundwork. It relies on tools that are inherently either not very scalable or have really challenging UX. But there are still components that can be formally verified if we are strategic about it. So I mostly focus this talk on the off-chain things, but some of the infrastructure does rely on smart contracts. So for example, bridges or L2s sometimes do use smart contracts that emit events for these events to be received or triggering some off-chain infrastructure as well. So for these contracts, we can formally verify that events are emitted correctly. We can formally verify that if they are paused, then they cannot be called successfully anymore. These are all things that we have proved for some of the L2s. And there are production-grade formal verification tools like well, our control, Certor Approver, Tolmach that are, that can deal with that. And then one more thing that I think we did at RV at 2019 was the verification of the Deposit 2.0 smart contract that stores $200 billion or something like that right now. So that is important to make sure that it is correct. And while formally verifying it, we actually did uncover some wiper bugs. And compiler bugs generally are really challenging to identify. So that is where formal verification does help identify issues that would be hard to find otherwise. And I think Certora, the guys from Certora also identified some compiler bugs by doing formal verification of smart contracts. If you go deeper, like beyond smart contracts, we can do things like formally verify equivalence between different implementations of EVM. That is one of the projects we worked on. We proved the equivalence between KVM, our formal model, and Nethermind's EVM Yule, making sure that the opcodes are implemented and represented similarly. And we did identify some places where that was a bit different. And we can also do that with other EVM implementations, like RVM, the Rust one, which is also one of the projects we were doing, which is very important because RVM powers a lot of ZK EVMs. So we actually would like to make sure that it works correctly. And then, yeah, of course, we can do things like we can model protocols, we can model consensus protocols and formally verify them. That is something we've done before, and that I personally believe is better done at the earlier stages of the development process. And yeah, finally, we can also select some specific components that are small for us to reason about them efficiently, like data structures, like important operations on data structures, and this sort of things. So I would like to wrap this up with some practical advice based on our experience at RV. So what works for us best is shorter engagements, or like sequence of shorter engagements, because as I've mentioned, it helps auditors stay focused. It allows some leeway for the protocol developers to actually fix issues between that, and with priority in the shorter audits given to complex, critical, new, important code, unsafe. So something that is very important for a human being to look at. Then we do recommend starting with defining specifications, threat model, invariants, putting together the specification basically, and using that to inform the review. So we do both AI review and manual review against these properties because that does add an additional dimension to the code review that we are doing, helping identify differences between the intent or specification and the code, not just vulnerabilities that are, present themselves in the code per se. We do recommend, obviously, building a fuzzing harness, and, well, first of all, because it does help identify issues, and then it also helps with the code getting evolved. If you can reuse it, then you can continue running this and see if that doesn't cover any new issues. Although the challenge with that is that it is very stack-specific and target-specific, for which we also should have a very good idea of what the project does. And then for formal verification, we'd recommend applying it selectively. It doesn't fit very well in this 6 to 8 week engagement, depending on what it is the formal verification that we are doing and what it is focused on. But yeah, generally speaking, of course, it does provide the best security guarantees out of all of this tooling. So yeah, cannot not recommend using it. And yeah, finally, we do use AI-assisted review, as I've mentioned, for extra breadth. It does help us look at the parts of the code base that just would be infeasible for us, for human beings, to look at. So it does help identify issues that perhaps we would not have been able to find otherwise within this very short time-boxed type of engagements. But it does work best when you do provide the specification. So yeah, highly recommend doing that. And yeah, that is it for my presentation. Thank you so much. I hope that has been helpful. And please let me know if you have any questions, if we have time for that.
Thank you. Thanks, Palina.